The reason Newton's idea of universal gravitation was so incredibly new and different was that it did not involve contact. It involved a field. Remember, we tend to think of forces as pushes or pulls, where we physically touch something or something physically touches us and that exerts a force. Gravity, Newton said, is not like that. Gravity is something that acts over a very large distance. It doesn't matter how far apart these things are. And so it's not a direct interaction. Instead, we say it's a direction or an interaction with a field. So if we have a central mass, and I'm just going to call it M for mass, around it, it energizes a region of space. And that region of space is capable of exerting a force on any other mass that comes into it, at least if it's a gravitational field. Electric fields also exist. They exert forces on electrically charged particles in it. Magnetic fields also exist. They can exert magnetic forces. Okay? So when we think of a field, it's really a region of space capable of exerting a force. And that's a new concept because we tend to think of things as requiring contact, but they don't. There's a few forces that act over distances. Gravity is one of them. Electromagnetic is another one of them. Strong and weak nuclear forces, they also act over distances. Okay, they act over incredibly short distances, whereas gravity can act over incredibly long distances. So what we're interested in is how much force will a mass out here feel? How much will it accelerate? What will it feel if it's this far, a unit distance r from here? How big is the gravitational field? Well, if we think about what the equation says, F equals m1, where this could be m1, the central thing, times m2, which would be the mass out here, divided by r squared, times the universal gravitational constant g, we can see that if the distance gets big, the force gets really, really small. The problem is it's dependent on that second mass that's out here, and we would like it not to be dependent on that. We want to know what is the size of this field independent of this mass. And so the way we do that is we say, well, let's just divide the mass out of there. Divide by m2, divide by m2, and we get the idea, the concept that field, which is actually going to be newtons of force per kilogram of mass, is equal to F divided by m, or it's just m of the central body, m1, times g divided by r squared. Okay? So instead of using the second mass in there, what we get is we get this thing that's just m1g divided by r squared. Now what does this tell us? Well, this tells us force per unit mass, force per kilogram, or newtons per kilogram if you'd like. And this is an interesting unit because remember, a newton is the amount of force required to accelerate 1 kilogram at 1 meter per second per second. And if we divide that by kilograms, that goes away, and this is equal to the units of meters per second, which is identically acceleration. There is a subtle difference between gravitational field and acceleration. Gravitational field tells me how much force every kilogram of mass experiences. Acceleration tells me the rate of change of its velocity. So we can use them interchangeably, but they are telling us they're different ways of analyzing sort of the same information. So if I want to know about the gravitational field of two objects, so here I have a little object way out here and two objects way out here, neither one of their gravitational fields matters. What we're interested in is what is the force they feel because of their proximity to this central body here. Okay, they're both the same distance away. Are they going to feel the same force? Well, no, this object is bigger, but they are going to be in the same field. Okay, so what that means is we divide out their m, their test mass, whatever it is, and we're just left with how much field strength is there. Okay, so if we're looking at the surface of the Earth, okay, well, at the surface of the Earth, we know that the acceleration due to gravity on the surface of Earth is 9.8 meters per second per second. Okay? Well, that actually tells us the field strength on the surface of Earth, okay, where the radius is just the radius of the Earth, r. We know that the magnetic or the gravitational field is equal to 9.8 newtons per kilogram. That is the reason why every object falls at the same or with the same acceleration on or near the surface of Earth. Because every kilogram of mass experiences 9.8 newtons of force. More massive objects experience more force, which causes them to accelerate with the same rate as less massive objects. They experience less force. Okay? So this field actually tells us that everything in the field is going to accelerate at a uniform rate at any given distance. Now, as the distance changes, that acceleration is also going to change. Okay? So what we end up seeing is, if this is the Earth, the gravitational field is really, really strong right on the surface of Earth. As we get further away, that gravitational field is less and less and less strong. So something, and even astronauts in space, though, orbiting the Earth, they're not without gravity. There is actually an acceleration due to gravity, and they're somewhere around 8 meters per second. Or that is to say that every kilogram of mass is undergoing or is feeling a force of 8 newtons. So the gravitational field is around 8 newtons per kilogram. The reason they feel weightless is because there's no normal force, right? These guys are accelerating towards the Earth and missing. They're in uniform circular motion. But there is gravity out there in space. You have to get a really, really long ways from Earth before even that gravity is cut in half.